last year and take a look at the amazing feat of engineering and technology that came to being in order to be able to get this ultimate luminosity. We will need new superconducting magnets, new superconducting cavities, an amazing technology in order to collimate the beam to get this ultimate luminosity, and superconducting links that have negligible energy dissipation over more than 300 meters of link. So it's a feat of marvel, and just another jump, just like it was from the Tevatron to the LHC, for instance. So I invite all of you to look at this technical design report. For the students in the audience, however, all of you old timers know this already, but I would like to remind you that luminosity comes at a price. Remember, luminosity is related to the number of interesting hadronic interactions, which are going to call events that the accelerator can deliver. Now, if you're interested in a process which has a cross-section sigma p, you know that the rate of events per second is the luminosity times this process cross-section. Now, you have this formula that if you have a proton bunches colliding head-on, there's a Gaussian profile in the transverse directions here. You have this formula here, which relates the number of protons in the bunches, the frequency of revolution, the number of bunches, and the width of the beams in both directions. Now, if we unpeel this calculation back a little bit, we divide by the number of bunches, we divide by the luminosity per bunch pair, we get the luminosity per bunch pair. If we again divide by the revolution frequency, we'll have the specific luminosity for one single bunch crossing. Of course, it's a stochastic process. Every single bunch crossing may give a larger or smaller instantaneous luminosity. If we now multiply this by the total PP cross-section, which is more or less 80 millibarns, but let's not get hang up in this number, we come to the total number of interactions per bunch crossing. So when you cross the two bunches, you have a total number of proton-proton interactions that happen in the same bunch crossing. And this is the so-called pileup. In the same bunch crossing, you have multiple proton interactions, and this makes the analysis, the acquisition and analysis of the data become much harder. So the pileup of events is the price you must pay for this high luminosity. Now, at the LHC, as you can see here on the bottom left, we had something like mu from 30 to 50, so 30 to 50 simultaneous events. There is a distribution, of course. For the high luminosity LHC, however, if you run the same calculations, you'll get that for the nominal scenario, you have 140 pileup events, which is more or less 3 times than what we had in the LHC. While for the ultimate scenario, we have 200 simultaneous pileup events. This is completely uncharted territory for hadron colliders, again, just like it was in the jump from the Tevatron to the LHC. Now, okay, we have this problem of pileup, and I'll show you that is really problematic in the later slides. But let's back up for a second. Again, okay, we need more luminosity, but what do we gain with this high luminosity? And the key thing is that if you look at the limit plots that we have already put out with the Hangzhou data, you will see that, for instance, for beyond standard model searches, new physics is going to be a rare process, even with this ultimate luminosity of 4,000 inverse femtobarn. So the limits are such that we'll need all of the data in order to get at least a glimpse of evidence of new physics. But on the other hand, this means that we'll have a much more important role for precision physics. So it's just like the old lab times again. You do extremely precise measurements of standard model parameters, you search for the most rare processes, and in doing that, you will have a hint of where the deviations could lie, if new physics could be lying on something like the oblique parameters at lab. Now, I'm going to talk about 3 examples that I handpicked. Of course, there are many of them, but that physics that can be done at the high luminosity LHC. Let's start with this one, WW scattering. So at high invariant mass, you can have WW to WW. And you all know this, but this scattering is one that is regularized by the presence of the Higgs boson, of the Higgs mechanism. Now, by doing a precision measurement of this, you can confirm the role of the Higgs boson in taming this cross-section. Or alternatively, you could search and find a different underlying electric symmetry breaking mechanism. How good is that? So in the run 2, we already have results for the same sign WW plus 2 jets. And with respect to the standard model expectation, we have something like 1.2 signal strength, but there are these errors here, which more or less come out to be something like 10%. But the key thing is that these are the completely inclusive WW measurements. If you go into the polarized same sign, which is what is really important for the electric symmetry breaking understanding, we didn't measure it yet, and we will not measure it with just the data that we'll take in the regular LHC. The doubly polarized one, we know that it's less than 1.17 femtobarn with 95% confidence level, and the singly polarized one, we have something like a 2.3 sigma. It's not even evidence yet. When we go to the high luminosity LHC, as shown here on the left, we'll be able to measure the complete same sign WW with 3% uncertainty, more or less, as you can see here. And the doubly polarized one, WL, will be very close to 5 sigma. So this is something that will allow us, the high luminosity LHC will allow us to completely unravel this process. Still on the same business of the Higgs boson, there are also the couplings. And the couplings, in particular, the couplings to the fermions, are a very exquisite prediction of the standard model. The question that we want to pose is, are the Yukawa couplings really proportional to the fermion masses? Or if we look at this plot here that was even shown previously, is this really a straight line? Now, from the run 2 results, we already have evidence for Higgs going to dimuons. But again, it has these gigantic uncertainties here, something like 40, 50%. And notice that this is the only second generation measurement that we can make at LHC. Higgs to CC bar, for instance, is extremely small, so it's probably unobservable even with the full luminosity of the high luminosity LHC. But we still have to search for it, because if we see it, that may again point into physics beyond standard model. Now, if we go into the high luminosity LHC, we'll see that we'll be able to bring the uncertainty down to something like 6.7%. So again, we will be able to see if this is actually a real line, if the Yukawa couplings are proportional to the fermion masses. One more time, the Higgs, and now the double Higgs boson production, which is something that has extremely, extremely rich physics, because there is 5 decay channels, at least, right? There are many of them, but these are the 5 main ones. And BB gamma gamma is probably the one that has the highest sensitivity. Again, we have results with the run 2 data, both in the non-resonant channel and in the resonant channel. And why do we have to split in between resonant and non-resonant? It's because, again, if we see a resonance, it may be indicative of physics beyond the standard model, but we need to measure this with the highest precision possible. So with the high luminosity, let's say we project this significance of 2.6 sigma. So we'll be on the edge of evidence of this process. And by measuring this, we can go back and see the triple coupling of the Higgs, and we'll be able to measure it with some reasonable uncertainty here, 68% in this interval here. So the high luminosity LHC will be writing one of the most extensive chapters in the Higgs boson and in general the standard model physics. But there is a caveat. There is the pile-up. And not only that, but there is also the dose. And this thing of pile-up and dose, they are going to be the leitmotif of everything that I'm going to talk to you now. Because the key thing is that we will have to rebuild our detector. We will want to extend our physics program to use all of the 4 inverse femtobarn integrated luminosity. And this means that we want to keep the detector performance. We want to have efficiency in reconstructing the object. We want to have good resolution to have the kinematics right. And we want to reject all the background, all the fakes. But the thing is that the high instantaneous luminosity, so the pile-up, means that we have all this horrible situation here. And these will become hard to untangle. So we need new detectors with improved granularity and timing information. I'll tell you more about this later. The second thing is that not only the instantaneous luminosity is problematic, but also the integrated one, namely the radiation that these detectors are subject to. You can see here that those that for the tracker and the end cap calorimeter, they're going to be exposed to an extreme amount of radiation. So their key parameters will degrade. The tracker and calorimeter that we have right now cannot withstand this dosage, so we have to change them. Last but not least, 3,000 or 4,000 femtobarn is a humongous amount of data. So we'll have to acquire and filter this data somehow. This means that we'll have to overhaul our complete trigger and DAQ systems in order to deal with this data deluge. Again, this is nothing new. We had such a jump from the Tevatron, for instance, to the LHC, but yet another jump like this. In order to cope with this, CMS prepared the so-called technical proposal for the phase 2 in 2015, which was approved, and then we started working on the upgrades of all of the subdetectors that comprise CMS. I'm not going to go through all of these slides, but every single subdetector has put out a technical design report by now, including the new detectors that we're going to build, like the new end-cap calorimeter and the new MIP timing detector that I'm going to talk about later. So at the end, I invite you to look at the reference. Let's start from inside, okay? Let's start with the tracker. The tracker is one of the subdetectors that suffers the most because it's the closer to the interaction point. So it is the one that has to deal with the highest multiplicity of particles and the highest dose. So it has to be radiation resistant. It has no other choice. And since we have so many tracks coming out because of the pile-up, we need increased granularity. But there is one other thing. One of the design choices that was made, and unfortunately it was made more or less the same both in Atlas and CMS, is that it turned out that there was a lot of material in front of the calorimeters. And as you know, this is not good for the resolution of the calorimeters. So the CMS tracker was redesigned in order to reduce the material. So you can see here on the bottom left, the material in front of the calorimeters in units of radiation length. So we want to reduce this as much as possible in order to preserve the colorimetric resolution. One other thing that this tracker will do that our previous tracker couldn't was that this will contribute to the level 1 trigger by the so-called PT module. So the outer tracker here shown in red and blue, it will be able to, through these PT modules here, to build stubs very fast at 40 megahertz that are compatible with tracks above 2 GeV and give this to the level 1 trigger to make calculations and decide to take the data or not. And last but not least, together with the new pixel detector here in yellow and green, we have this extended acceptance all the way to eta less than 4.0. So a completely new redesigned and better detector. Here are some of the geometry and parameters. Our inner tracker is going to again have 4 barrel layers, just like the phase 1 tracker, and 8 small disks plus 4 large disks per side with pixel sizes which are smaller than the ones that we have now. The outer tracker instead, we have 6 barrel layers, 5 disks per side, and in total we will have something like 50 million strips and 180 million macro pixels in the outer tracker. So a much higher granularity than what we have right now in our tracker. Are we able to put it into good use? And the answer is yes, as you can see here in slide 19. I'm just going to show you this particular plot that has the tracking efficiency as a function of the simulated track PT. This is still done in the same way that was done in phase 1 with combinatorial Kalman filter, but that there are other approaches that we are evaluating, like segment linking and MK-fit algorithms. Again, I invite you to look at the TDR to better understand them. For the combinatorial common filter, we have the same iterative approach where we build first the high PT tracks, then the low PT tracks seeded by quadruplets or triplets. And you can see here what every iteration does. And the bottom line is that for 900 MeV and above tracks, we have more than 90% efficiency and completely uniform in pseudo rapidity. So extremely high efficiency, just like in phase one. But even for low PT tracks, like 300 MeV, we still have some reasonable efficiency. I'm not showing plots about vertex, but I'm going to tell you that again, we manage, even in the high pileup configurations, reconstruct 3/4 of all the vertices, and in more than 90% of them, we're able to correctly identify the hardest vertex of the bunch crossing. Oops, sorry. So changing gears, but still talk about silicon detectors. Let me talk about the other new detector, which is our high granularity calorimeter that we're going to put on the end cap. Again, same requirements. It has to have good radiation tolerance, but also it has to have very, very fine lateral and longitudinal granularity for the same reason that the tracker does. We want to reconstruct all the particles that go through the calorimeter with very good efficiency and resolution. And we want it to be dense because we want the shower, the hadronic and electromagnetic showers, to be compact and well contained within. It also has precision timing, and it will also contribute to the level 1 trigger. It couldn't be different. But I'm not going to these details. I just want to draw your attention to the fact that even though it's built as an integrated calorimeter, it has both an electromagnetic and a hadronic section where we have silicon for the whole electromagnetic calorimeter and silicon scintillator sections for the hadronic one. And it's a layered calorimeter. So you have all of these layers that have that do the measurement of the particles. So this is a sampling calorimeter. With good radiation length and interaction length. Now, let's talk about these layers in a little bit more detail. These are the sensors of the high granularity calorimeter, okay? The silicon sensors, they come in two varieties, low density and high density, and it's a total of 620 square meters of silicon. And each one of these cells here then becomes one of the green cells here in the layer that's shown below. So the key thing is that the granularity is extremely high. And then you have, of course, again, millions of channels for the silicon and hundreds of thousands of channels for the scintillator. Why do we need that? It's just like a gigantic tracker. And it also will have resolution. Why do we need to have measure not only the energy, but also the position with such good precision and the timing with such good precision? And the answer is that the high granularity calorimeter is going to be an imaging calorimeter. So if you look here at this simulation, you will see that we'll actually be able to X-ray the whole shower as it goes through the calorimeter. And then we'll be able to fit all of this information into our particle flow algorithm that will be able to reconstruct jets with the highest precision. And you can see here how it works. See, we're able to, we have the tracks from the tracker, of course, but the calorimeter clusters are also kind of like tracks. So you're able to see the shower as it develops in the calorimeter. And this is a completely new way of doing calorimetry. But Thiago, this looks extremely complicated. Are you actually able to reconstruct this? And the answer is yes. So this is from the test beam already, a 32 GeV electron in prototype with, I don't know how many layers here, sorry, but 15 interaction lengths. And there are 2 rounds of reconstruction. First, we cluster the energy in one of the layers, collecting direct heat, and this is based on the cell energy density, which is a complicated formula that I'm not going to go into. But the key thing is that this algorithm that we built, it is linear with the number of rack hits, and this is important because there are tens of thousands of rack hits in each layer, and it's extremely easy to parallelize. And it's important because then we would port this algorithm to GPUs. More about that later. Then to link the different layers, we have the so-called iterative clustering, where we have these tracksters which link the different depositions, and this is all based on cellular automaton pattern recognition. The key thing is that you iterate, and in each iteration you build some kinds of particles in the shower. So you have electromagnetic but tracker based, so something that aims to reconstruct electrons, something that aims to reconstruct photons, charged hadrons, and neutral hadrons. And with that, we're able to almost do particle flow naturally in this calorimeter. Does it work? And the answer is of course, is under development, but seems to be working surprisingly well. Of course, electromagnetic showers are more or less simple because they are by nature well contained. And you can see here both, you can see here the resolution plots, but these are only for a toy reconstruction. The electron and photon group in CMS is doing full gamma reconstruction already brainstorm, but this is not ready yet. The hadronic showers are a bit more complicated because they have this branching structure where you have high depositions that are sort of linked to the main shower. But the initial approach with just a single trackster for the whole shower is promising. You see here the resolution again. So this new detector will probably be extremely hard to reconstruct, but we have very good results already. But then, of course, it's the compact muon solenoid, so we have to have something for the muons as well, right? So let me talk about the phase upgrade of the muon detector. All of our detectors that already exist, the drift tubes, the CSCs, and the RPCs, they are going to be upgraded in the electronics side in order to cope with the high-luminosity LHC conditions. But we'll also have enhancement for the forward muons here. So let me guide you in this plot of the geometry here. First, we'll have improved RPCs that are here in purple that will give us more redundancy. And what's improved? That means that they have short electrode recovery and reduce the total charge discharge. So they actually have better timing resolution, which will help in the reconstruction. Then we also have gen detectors. We have GE11 and GE21 here in red, which again, they give better redundancy on the end cap region. And this particular redundancy is good enough that we'll be able to improve our level 1 muon triggering in the end cap. It's very hard to do level 1 muon triggering in the forward region for the fact that the rate goes up too high. So it's hard to control the trigger. But with the gem detectors there, it will become easier. Last but not least, we have ME0 that sits here in orange, and it will extend our muon coverage up to 2.8. So again, a much improved detector. How's the performance look like? We see here that we extend, of course, we extend the acceptance, and even in the situation where we have aging, we're able to manage an extremely high efficiency, and this is both reconstruction efficiency and trigger efficiency, as well as lower trigger rate. Thiago, but what does this give us in terms of physics, which is what we care about? And this is the key thing. I'm going to just tell you about three things. This will increase the Higgs ZZ for mu, so the golden channel signal strength. This will allow us an improved resolution in the measurement of the weak angle, and this will allow us to make a much better measurement of the top quark mesh using the strict channel here, where you have top to J psi plus muon, so you can have something that correlates with the top mesh just for the tri-muon invariant mesh, and with much better resolution than you had in phase 1. Moving on, we also have a MIP timing detector. Why do we need that? We're going to measure the production time of minimum ionizing particles. Remember, the bunches themselves, the proton bunches themselves, they are wide. They have this length on Z. So when they cross, the interactions in a single bunch, they are spread in time, but not that much. It's an RMS of 200 picoseconds. But if we manage to get this additional handle on the interactions, it may help us mitigate the pileup effects. So we have two layers. We have the barrel timing layer and the end cap timing layers here with litho-C crystals. And we have some information here on the readout, but I would just want to draw your attention to the clock distribution system. Remember, the RMS here is 200 picoseconds. So the synchronization of this detector has to be very good. The jitter of the clock has to be around 10 to 15 picoseconds at most. Look at what this detector can do for us in slide number 28. So in the X coordinate, you actually have the Z of the vertices, and in the Y, you have the time. So imagine that if you don't have the time of the vertices, all of these, you just have the yellow vertical lines, and you have to disentangle the vertices by disentangling those lines. Okay, it's doable, but isn't it much better to add another dimension where the vertices spread, and then you have a much better idea of which track came from which vertex and which particles came from where? I think the plot speaks for itself. So very quickly, the timing resolution of the MTD is going to be something around 40 picoseconds, and it's new, but it will degrade with radiation, of course. What does this buy us? This buys us three things. First, an improvement in net resolution, and this is huge because first, it allows us to do important measurements like Higgs to tau, where you have intrinsic missing T, but all the BSM searches, SUSY, dark matter, will enjoy this enhanced resolution. The Higgs production that I said in the beginning is going to have plus 20% signal yield. So inching ever close to the 3 sigma. And for our friends in heavy ions, you'll be able to have particle ID, as shown here on the top right. So this detector will give us new capabilities that are hitherto unprecedented in CMS. But there is a problem. There is a lot of data to be taken. And 7.5 10 to the 34 luminosity is not something that's easily dealt with. So we have to improve our DAQ, we have to improve our trigger. In CMS, we're going to choose to retain the two-level trigger approach, so level 1 in hardware, high-level trigger in software. And let me quickly tell about our phase 2 upgraded level 1 trigger. First, the output rate of the trigger will go up together with the luminosity, so 750 kilohertz. But in order to deal with the complicated events, remember the pile-up, we will have to increase the latency of the trigger from 3.8 to 12.5 microseconds. And this increase of the latency in particular is what drives a lot of the changes in the electronics in all of the detectors. The level 1 trigger will be able to, again, read the calorimeters and the muon system, but unlike in phase 1, we'll be able to read the ultra tracker information as well. And then we will have these 4 independent data taking paths here directly from the calorimeter, directly from the muon, directly from the tracker, and this 4th one, which is called the correlator and particle flow. What? So this is the big thing of the level 1. Let me just highlight these 3 things. First, as I said, we'll have track trigger. So from the stubs from the outer tracker, we'll be able to run this hybrid tracklet plus Kalman filter track finder. The tracklet is where we put together stub pairs, and then you use this stub pairs as an input to a Kalman filter track finder. This is already described in the level 1 TDR, but just for tracks that come from the primary vertex. But we will be extending it for the displaced trajectories. Then, since the FPGAs nowadays are much better, we'll be able to have this correlator layer that will be able to run extremely sophisticated algorithms, like the aforementioned particle flow at level 1, but even also machine learning, which is something that was unthinkable at the beginning of the LHC. And we will also have, since we have all this high-level information already, we'll be able to do 40 megahertz scouting, where we save these candidates here, these intermediate streams, to do not only diagnostics and monitoring as we must, but we'll also be able to do physics with these level 1 particle flow candidates. So again, opens up a completely different avenue of research. I'm quickly just showing you the plots of rate versus PT threshold for all of the objects. And I just want to draw your attention to the fact that in all of them, when you have track-matched quantities, like track-matched muons, track-matched electrons, and so on and so forth, and PUP-tau, which is particle flow tau plus pileup mitigations, you have much lower rates, which in turn allows us to have much better PT thresholds. So we are also in very good shape here. In the level 1 TDR, we already went a step above, and we wrote the so-called phase 2 simplified level 1 menu. So even now, 10 years before the beginning of the data taking the High-Luminosity LHC, we already have a preliminary idea of what the trigger menu is going to be. And it's compatible with all the phase 2 requirements. We have 450 kilohertz output, and we have safety margin with respect to the target, more or less 40 trigger algorithms. And then we're going to extend it with standalone leptons at high eta, soft muons, pure level 1 tracks for light mesons, displaced vertex. The level 1 trigger has become so powerful now that honestly the sky's the limit, which is very good. But then the thing is that it brings us problems, or the good kind of problem is still a problem at the next level of the trigger, which is the DAQ HLT. So you all know this, but again, for the students, the DAQ is the system that takes care completely of the data as it comes from the detector, does the time decoupling, because remember the LHC is something that is bunched, so every 25 nanoseconds, does the detector readout, and does the data reduction to save in offline. The DAQ takes care of the local storage and the transfer to offline. The physics part of it, in a sense, is the so-called high-level trigger, where we do the selection of the events of interest, and we are aiming again for a reduction of 100 to 1 with respect to the level 1, which is harder, right? Because the level 1 is smarter now. So it's harder to do this reduction. And of course, we have to do this within an envelope host of the computer resources that are available. I quickly want to share with you the key parameters here. Again, 750 kilohertz of level 1 output, which is the HLT input. The event network to build the event for the DAQ is going to be astonishing 50 terabits per second. And the HLT output is going to be 7.5 kilohertz, and something like 50 gigabytes per second. So it's again a gigantic data acquisition system. Let me quickly go to the technical and engineering part of the DAQ. It's going to be all optical, 50,000 high-speed front-end optical links. The data rate, as I said, is something like 60 terabytes per second. The event size is going to be much larger, of course, than the LHC, again, for the simple fact that the events are much more busy. They are much more, they have 200 pileup. Some highlights that I want to tell you. First is that we'll have a unified detector readout, in the sense that everybody is going to be using the same technology. So everybody is going to be using ATCA form factor. Since again, we have much more powerful FPGAs, we'll have this dual function board, the DTH400, which will not only take care of the DAQ data aggregation, but also the timing trigger control and distribution part. So the control and the workhorse in the same board. This 60 terabits per second is not trivial to do. The technology we're choosing is so-called remote direct memory access, RDMA over converged Ethernet. And the one very interesting thing is that we'll have heterogeneous HLT nodes. So up until run 1 and run 2, we had only standard off-the-shelf commodity hardware. And this was okay, but for the run 4 and beyond, this is just regular. Servers are not going to cut it. We need to have the best price performance ratio, and this means GPUs. Let me quickly tell you about the physics objects path and menu of the high-level trigger. And one interesting thing in CMS is that the physics objects that we build in the trigger, they use the same algorithms as offline, they use the same frameworks, MSW, but we add a lot of emphasis on the execution speed. Of course, you have to manage the three things. You have to have high efficiency, low rate, and high speed. The HLT paths are algorithms that target a given final state, and they are one of these vertical columns here, where you have a producer and filter in a sequence, so that the producer makes some calculation on the event, and the filter then asks if this quantity is above or beyond the threshold. Why do we build like this? Because we have the so-called early filtering, where we don't want to waste time making calculations for events that are already lost. Then the menu is a collection of these paths, and the variables are reused among them. Why do I draw attention to this? Because this whole thing is multi-threaded. So we are able to process many events in parallel, and we are able to run calculations for the same event also in parallel. And this is a key thing for the GPU capabilities that we want to implement in the trigger. I just want to flash this slide again. This is the efficiency of the high-level trigger algorithms, and you have here the turn-on curves for taus, for electrons, for muons, for jets, and for B-tagged jets. The key thing is that, as I show you here in slide number 38, we are able to keep the rate and timing compatible with the phase 2 requirement, so something like 50% of the ultimate target again, with the single object-based paths that comprise what we call it again, the phase 2 simplified HLT menu. So again, we wrote the TDR and we went a step beyond to already have an initial proposal on how our menu is going to look 10 years from now. We have more or less the same structure, so we have paths that select on single and double muons, triple muons, so on and so forth. And the rate is again dominated by some heavy hitters like the single electron and single muon isolated ones that all by themselves take 1 kilohertz of rate. Remember, 1 kilohertz of rate is more or less the total HLT rate in the high-level trigger right now. For the timing, the key factor is all of our algorithms are going to be ported to be GPU able. In run 3, we're already going to do that, by the way, okay? In run 3, just offloading the inner tracker, we're going to go from 330 milliseconds to 250 milliseconds. So something like a 20% improvement in timing. For the phase 2, we are expecting to offload something between 50 and 80% of the total code to GPUs. That's exactly what you heard. Most of the code will be running on GPUs. That's the challenge of phase 2. That's not all. We'll need to improve the code by itself as well. But again, we have 10 years to get these additional performance improvements. Next to last, we have the so-called BRIL project, which is the phase 2 beam radiation, instrumentation, and luminosity. And again, the leitmotif is that we have to monitor the beam radiation in order to protect and understand the lifetime of our subdetectors and to measure both the real-time and the integrated fluence that these detectors are suffering. And these two things are very closely related. We are also going to measure the luminosity. We always do, but now we are upgrading the system. And we are going to measure both in real time in order to optimize the running scenarios, but also the all-important number, which is the integrated luminosity. That's a key input to all the physics we do. So here we're targeting another 1% uncertainty. I'm not going to read through the table, just some highlights. We're going to have plenty of luminosity measurements. The ones that are going to be more improved are the ones from the inner tracker handicap pixel. We have also luminosity from the outer tracking. We're going to have a new luminosity detector, the fast beam conditions monitor, and we're going to have some neutron monitors for the fluence. Again, the TDR is about to come out, just as the DAQ-HLT TDR. For offline in computing, there is a lot of work to be done. I'm just going to quickly go through these plots here. In the three that are not pie charts, you have in gray the increase of resource available both in all of CPU, tape, and disk, assuming 10 to 20% increase, that's the range. And in blue, you have the needs of the experiment for 2 scenarios, which, as you can see, are larger. And the key thing is that this is under the assumption that no R&D is done. So our work will be to do the R&D in order to bring the blue curves to fit inside the envelope. And this goes into a big discussion as well into the computing for the high-level trigger as well. Where are we going to attack? We have to attack the event size, which, as you see on the pie chart on the right, is essentially the raw. And on the left, the need for computer and time is essentially the reconstruction. Reconstructing all these high granularity detectors takes a lot of time. So I'm arriving to my conclusions, and let me again hammer on these points. This high luminosity configuration is the way that we're going to get to do the full exploitation of the LHC. We're going to complete this cycle, lab, LHC, high luminosity LHC. And we need the full luminosity, the 4,000 events photobarn, in order to do the most extensive search and the most precise measurements. And this allows us to fit to, as much as we can, finish the elucidation of the electric symmetry breaking and to measure the characteristics of the Higgs boson. These high luminosity conditions are going to be the harshest to date, highest event rate, highest pile-up. The detectors will suffer a brutal dose of radiation. And in order to cope with these conditions, we'll need to do the phase 2 upgrade. And this will allow us to profit from this high luminosity era by keeping, and in some cases even improving, the performance that we delivered in phase 1. So I would like to thank all of you for your attention. Here are all of the reference used for this talk. And if you have any questions, please feel free to contact us at our email. Thank you very much.
Thank you. Thanks a lot, Thiago, for the very nice and complete talk. And we are now open for questions. So we have time for questions. So if you have one, please raise your hands. This one from Marcia Gali. So, second.
Yes, I was trying to unmute. So, hello, Thiago. Congratulations for the very nice presentation. Well, my question is about the aging of the tracking detector, because it will be very close to the beam. And then with all this radiation, I mean, how long will the tracking detector, mainly in the inner layers of the detector, how long will it last?
Thank you very much, Marcia, for your question. And this is something that we already had in mind when designing. So I didn't say that, but I'm going back all the way to the tracker. And the key thing is that, again, the inner part that is highlighted here in green and yellow is designed in such a way that it's easily taken out and replaceable. So the plan is to take it out in between run 4 and run 5 in order for it to be able to extend another round.
Very clever. Thank you.
Very good. Any other question, Thiago?
So maybe I can ask some question to Thiago. Usually when we are in front of the beginning of an upgrade program in such a long view like you are showing many years, usually we have this impression that everything is going to work fine. And then when we start to do things and when we go to the middle of the period that we have in front of us, we realize that we have a lot of things to reshape and a lot of things to rethink about. So where do you think, so from your presentation, apparently we could conclude, oh, everything is under control, we are in good shape, nothing bothers us, we are going to achieve all this. But actually, we know from the experience that is not the case. Some of the things are going to disrupt, and some of the things are going to be redesigned because of something. Where do you think is the main point for this? Where you worry about it? Is there anything, or everything is really under control?
That's a tough question you ask me. Eh? So, I honestly would say it's this plot that I showed here in the end, okay? It's already here. We know that we will need a lot of R&D in order to bring the amount of computing that we will have available here. We'll need a lot of R&D to bring this blue line, which is what we need, to this gray interval, which is what we hope to have available. What kind of R&D is this? It's better algorithms, right? It's essentially tuning the algorithms, porting to GPU, making parallelizable, and not only that, but also having machine learning as one more tool in the toolbox. Now, I would like to say that I am extremely grateful that CMSW has been running multi-threaded and easily parallelizable, at least since 2016 or 2017. So this makes our job much easier on the sense that we already do threading. So doing 100 and something threads for GPU is not that large of a step. But to answer your question, these needs of offline and computing are what keeps me awake at night.
Thank you.
Okay, great. Any other question? If not, I think we can, thanks again, the speaker, Thiago, thanks again for the very nice talk. So, and we can, yes, and we can close this section. So, bye-bye to everyone.
Thank you very much for the invitation. Thank you very much for your attention. Cheers, bye-bye.
Ciao.
Bye.
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 Bye.